We begin our study of aromatic ions by considering the question, are there or can there be any aromatic compounds with an odd number of carbons? Well, we know how many electrons an aromatic compound is going to have. It's going to have 4n plus 2 pi electrons. And mathematically, 4n plus 2 is always going to be an even number. So that means aromatic compounds will have to have an even number of pi electrons. It's also not clear how a molecule with an odd number of carbons can have sp2 hybridization and a p orbital on every carbon. So let's look at an example. Let's consider cyclopentadiene. Well, one carbon, carbon 5 in the proper numbering scheme, will have 2 hydrogens on it, the one at the top, and sp3 hybridization. There are clearly not enough carbons to have 3 double bonds in cyclopentadiene, so this molecule is definitely not aromatic. However, what about the Cyclopentadienyl Anion? It has a single hydrogen, a lone pair, and a negative charge on C5 that had 2 hydrogens on it in the neutral compound. So based on traditional VSEPR arguments, the hybridization at carbon 5 should remain sp3, and the lone pair should go into, therefore, an sp3 hybrid orbital. However, the hybridization could also be sp2, in which case the lone pair would go into a p orbital. If this is the case, the electrons of the lone pair will now contribute to the pi electron count, bringing it up to 6. So there's 4 pi electrons coming from the 2 double bonds, and then there's 2 more coming from the lone pair, which brings us up to 6, and therefore this ion is aromatic. So here's the orbital picture of this situation. So neutral cyclopentadiene, as you can see, has an sp3 hybridized carbon, so there's only 4 p orbitals being contributed to the pi system. We're skipping a carbon, so therefore it's not going to be aromatic. But for the cyclopentadienyl anion, we have a p orbital on each of the 5 carbons, and one of those p orbitals contains 2 electrons. Therefore, it will contribute 6 pi electrons, which is a Huckel number, and be aromatic. We can also draw resonance structures. Okay, so we can draw 5 resonance structures for this ion, in which the negative charge can be delocalized onto each of the 5 carbons. Notice the curved arrows here, which show that to get from one resonance structure to the next, the minus charge actually moves 2 carbons and not 1 carbon. And then also drawn at the top here is the way we would draw the resonance hybrid. So just like we have a structure for benzene where you put a circle in the middle of the 6-membered ring, you can put a circle in the middle of the 5-membered ring for the cyclopentadienyl anion. You just have to put a negative charge in the center to show that it is an anion. Okay, so how does this aromaticity of this ion affect reactivity? That's always a question that we want to keep in the back of our minds. The answer is that cyclopentadiene is unusually acidic for a hydrocarbon. Okay, so if you go look at your pKa tables, the hydrogen bound to C5 has a pKa of 16. It has essentially the same pKa as the OH of water, whereas most hydrogens on an sp3 carbon will have a pKa greater than 40. So assuming you use a strong enough base, you can deprotonate cyclopentadiene to give the cyclopentadienyl anion. The enhanced stability, the enhanced acidity is due to stabilization of the anion left behind after a hydrogen is removed. And as you can imagine, aromaticity would be the ultimate stabilization of an ion. Okay, so that's an example of a 5-membered ring, odd number of carbons, in which you can have aromaticity as long as you put a charge on it. What about a 7-membered ring? Well, to get a 7-membered ring with 6 pi electrons, remember 6 is the Huckel number, we need to have a cation, not an anion. Okay, if we had an anion with 7 carbons, you would actually end up with 8 pi electrons, which of course would be anti-aromatic. So the cation that we are interested in is the cycloheptatrienyl cation. Now that's a mouthful, cycloheptatrienyl. Try saying that a few times fast. So this cation actually has a better name. It's called the tropylium ion. It rolls off the tongue a little bit better. So just like in the case where there were 5 resonance structures for the cyclopentadienyl anion, there are 7 resonance structures for the tropylium ion, and the positive charge can be put on each carbon of the ring, essentially saying that all 7 carbons of the ring are essentially the same. Once again, just like in the case of pushing the arrows to get from one resonance structure to the next for the anion, the positive charge moves 2 carbons around the ring with each successive resonance structure, except in the case of the cation, we need only 1 curved arrow to get from one resonance structure to the next, rather than the 2 curved arrows that we needed for the anion. Okay, so our orbital picture now is you have 7 p orbitals that are part of the aromatic system that can overlap to form pi molecular orbitals. 6 of those have an electron in each one of them for the carbons that are formally part of the double bonds, and the 7th p orbital is vacant. It's okay to have a vacant p orbital, just like it's okay to have 2 electrons in a p orbital, as long as you get up to a Huckel number. So the vacant orbital means that we have only 6 pi electrons. Just like we drew a resonance hybrid for the cyclopentadienyl anion, we can draw a similar circle inside the heptagon for the tropylium ion, except now we have to put a positive charge inside it instead of a negative charge, because it's a cation rather than an anion. Okay, so this structure, this cation, meets the criteria for aromaticity. It's planar, there's a p orbital on each carbon, and in fact this cation is so stable that it can be isolated and stored. You can actually buy tropylium with a suitable counter ion. You might recall that most carbocations are so unstable that they are very short-lived reactive intermediates in the middle of a mechanism. So the aromaticity most definitely imparts unusual reactivity to this particular structure. Now, the other thing is, in order to generate the tropylium ion, it can still be generated from a neutral precursor. But recall that carbocations must be generated by loss of a leaving group, not by deprotonation. If you remove a proton, you leave those electrons behind. We're not going to lose H- as a leaving group. That's way too strong of a base. So as a result, we generate the tropylium ion from something like cycloheptatrienyl bromide. So note here that the neutral compound, the starting material, is not aromatic because the top carbon is sp3 hybridized. But once we lose the leaving group, we generate something that is aromatic as the cation. So this would be a particularly facile leaving group to remove. Furthermore, because you cannot generate a cation by deprotonation, cycloheptatriene, the hydrocarbon, does not have any appreciably acidic hydrogens. The only way you can generate the cation is by loss of a leaving group. Okay, so this generalizes our definition of aromaticity a little more than just neutral hydrocarbons. In the next lesson, we will generalize our definition even further and talk about the important concept of aromatic heterocycles.